Hello, everyone, and welcome to York Observatory's weekly Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Maheen, and I'll be one of your hosts this evening. I'm joined by Nakul, Arfa, Dhyan, and Sana. We are broadcasting live from the Alumni Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle at York Observatory and on Facebook at Alumni Carswell Ops. Tonight, we've got a great presentation about the James Webb Space Telescope. With the upcoming spectroscopic data and color images in July, it is the best time to talk about the amazing telescope and the doors it will open for astronomical research in the future. Before we get started, I would like to mention that the observatory at your campus is in Toronto, and we would like to welcome all of you to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many indigenous nations. The area known as Takaranto has been taken care by the Anishinaabe Nation, the Haudenosaunee Confederacy, and the Huron-Wendat and the Métis. It is now home to many indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Welcome again, everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week. Tonight, Moon reaches apogee, which is the farthest point from Earth in its orbit. It will then sit 406,580 kilometers away. With no interference from the Moon, it is a great opportunity to look at noctilucent clouds or NLCs. You may ask, what are noctilucent clouds? These night glowing clouds form high up in the atmosphere and are created when ice particles form on high flying dust. They can be a treat to catch even for astronomers, even though they usually hate clouds. On Thursday, June 30th, ninth magnitude comet C/2017K2, also known as Pan-STARRS, is gliding through a rich constellation of Fucus. Since this region is already well above the southeastern horizon at sunset, it is on view all evening. Just wait for it to get a little dark outside before you comet hunt. Several star clusters are nearby which can be used as a guide to spotting this comet, including a fourth magnitude open cluster IC4665, which sits just northeast of Seberlai, and also the seventh magnitude globular cluster Messier 14 just under 6 degrees southeast of the comet. There is also an opportunity to view some planets on Friday, July 1st. Venus creates a 6 point of light framing Taurus, the bull's face, this morning. An hour before sunrise, the planet stands just over 4 degrees north-northwest of Aldebaran and 1.7 degrees northeast of Epsilon Tauri. Mars is also visible before dawn this morning, shining at a magnitude of 0.4 less than 1 degree southwest, which is to the upper right of fourth magnitude Omicron Piscicum. Mars will rise around 1:30 a.m. local time. Mars will brighten slightly throughout July, though it remains to appear small. Moon is currently in a waxing crescent phase and isn't visible at all. As mentioned before, some of the stars visible tonight include Arcturus, Vega, and Altair. You should be able to spot them with the naked eye or binoculars. So now we should get started with the presentation. First off, we have Nakul, who will give you an introduction on what JWST is.
Hello all, hope everyone is doing well. This is Nakul and I'm going to give a brief intro about the James Webb Space Telescope. So the JWST is an infrared telescope basically with a greatly improved infrared resolution, and we can say it's the most powerful telescope ever launched into the space. It is expected to open doors for many discoveries and research opportunities in the field of infrared astronomy and cosmology. The goal of the mission are to search the light from the first stars and galaxies that formed in the universe after the Big Bang, to study galaxy formation and evolution, to understand star formation and planetary formation, and to study planetary system and origin of life. This space mission is led by the National Aeronautical and Space Administration in collaboration with European Space Agency and Canadian Space Agency. The Space Telescope was named after James E. Webb, who was the administrator of NASA. The Space Telescope was launched on 25th December 2021 on ESA's Ariane 5 from Kourou, French Guiana. The total cost of this project was 9.7 million USD approximately. And next, we're just gonna see the location and orbit of the JWST. JWST operates in a halo orbit, circling around the Sun at the Sun-Earth L2 Lagrange point, which is approximately 1.5 kilometers beyond its object. I mean, this telescope is not inside its orbit, but it's outside. And next, we're just gonna see the size and structure of the JWST. JWST's primary mirror consists of 18 hexagonal mirrors like a honeycomb, made up of gold-plated beryllium, which makes up to 6.5 meter, which is enough to collect more light, and more light collecting area leads to the discovery of many space objects and also answers many astronomical related questions. Gold coating provides infrared reflectivity and durability. The focal length is 131.4 meter. The mirror should be kept under 50 Kelvin in order to prevent damages. It also has a sun shield protection to block heat so that the temperature on the mirror won't get disturbed. The wavelength of the mirror is between 0.6 micrometer to 20.3 micrometer. And next, now I'm going to read out some functioning elements of the JWST. JWST has 4 elements: spacecraft bus, integrated science instrument module, sun shield, and optical telescope element. First, spacecraft bus. It provides electrical power, computing resource, cooling capability, and structural stability. And next one is integrated science instrument module, ISIM. It holds 4 scientific instruments and a guide camera. The 4 scientific instruments consist of near-infrared camera, near-infrared spectrograph, mid-infrared instrument, fine guidance, and near-infrared imager and slitter spectrograph. Near-infrared camera, NIRCam, is an infrared imager which will have a spectral coverage ranging from 0.6 micrometers to 5 micrometers. Near-infrared spectrograph, NIRSPEC, performs spectroscopy over the wavelength from 0.6 micrometers to 5 micrometers. Mid-infrared instrument, MIRI, measures mid to long infrared wavelength ranging from 5 micrometers to 27 micrometers. And the last one is fine guidance sensor and near-infrared imager and slitter spectrograph, FGS and NIRISS. Is used to stabilize the line of sight of the observatory during science observation. And the next one is sun shield. It's a thermal control system and protect the mirror from heating. And the last one is optical telescope element, which consists of primary and secondary mirror of the telescope. And next, handing it over to Arfa, who will be explaining the difference between JWST and Hubble telescope.
Thank you so much. So today I'll be talking about the Hubble and JWST. A quick recap of what the Hubble is. Well, the Hubble Space Telescope, it's a space telescope that was launched into low Earth orbit in 1990 and remains in operation. JWST, which we refer as Webb, is wrong to be called a replacement or successor of Hubble telescope. Webb's capabilities are not the same as Hubble to begin with. One of the major differences is Webb will be looking at the universe in infrared. It uses 4 main scientific instruments to capture the beautiful images and spectra of astronomical objects. These instruments provide wavelength coverage from 0.6 to 28 micrometers or microns. 1 micron is 1 into 10 raised to power minus 6 meters. So basically, Webb's instruments are working from 0.7 microns to a few hundred microns, which include the infrared and a part of visible electromagnetic spectrum, let's say red and yellow visible spectrum. Now, in comparison, Hubble, on the other hand, can observe a very small portion of the infrared spectrum from 0.8 to 2.5 microns. Its main focus is on the ultraviolet and visible part of the spectrum. Now, the question arises, why are infrared observations so important to astronomy? Our universe and galaxy have hidden many stars and planets behind the dust which absorb the visible light. However, infrared light emitted by these regions can penetrate this dusty shroud and reveal what is inside. Moving on to the sights. Webb's one of the most famous features is its primary mirror, which has a diameter of approximately 6.5 meters, which is significantly larger than the mirrors installed in any other telescope. The Hubble telescope mirrors are only 2.4 meters in diameter. Not to forget, Hubble's corresponding area is 4.5 meters square, where Webb has 6.25 times more collecting area. What this means is that the Webb will have a larger field of about 15 times more than the NICMOS camera on Hubble. Moving on to the orbit. Not only is the composition or the technology used in these telescopes different, it is also how these telescopes orbit. Earth is about 150 million kilometers from Sun, and the moon orbits the Earth at a distance of 384,500 kilometers. Now, the Hubble telescope only orbits the Earth at an altitude of 570 kilometers above it. The difference comes here. Webb doesn't orbit the Earth. It will rather sit at the Earth's Lagrange point, which is 1.5 million kilometers away. When the Webb reaches the L2 point, its solar shield will be responsible for blocking this sun that the light is reaching by Sun, Earth, and the moons. It is very important to protect it from those lights because Webb needs to stay cool since it's an infrared telescope. Webb is orbiting the Sun, but in relation to the Earth, it will stay in a fixed position. Last but not the least, how far will the Webb see? Astrophysics is quite confusing yet surprising sometimes. A quick example for everyone is what I'm going to explain next. It really did confuse me for the first time. Now listen to me carefully. Because of the time it takes light to travel, the further away an object is, the further back in time you're looking. The picture I've added on this slide illustrates various telescopes and how far back are they able to see. Where Hubble can see the equivalent of toddler galaxies, Webb will be able to see baby galaxies. Why is that? Because of its infrared telescope. The universe and thus the galaxies in it is expanding. When we talk about the most distant objects, Einstein's general relativity comes into play. This tells us that the universe expands, so does the space between the objects that actually stretch between the galaxies to move away from each other. Even if there is any light in that space, it will also stretch, which will also stretch further to the wavelengths of the light to longer wavelengths. This makes the distant objects very dim or invisible at visible wavelengths or light. That light reaches us as infrared light. Now, infrared telescopes like Webb are ideal for observing these early galaxies. Now, on to Dhyan now. Thank you.
Thanks, Arfa. So by now, you guys all know about the telescope. But now let's talk about the future of this amazing telescope and the kinds of doors it'll open for all of astronomy. So initially, James Webb was only expected to last about 5.5 years. But after its successful launch, it turns out that we might have enough fuel to support about 10 years of scientific operations. This means we'll have almost double the time to make new discoveries and perform world-changing research. This crazy telescope was first formally proposed in 2001, and it has four main objectives: to trace the evolution of galaxy formation, to study star and planetary system formation, to characterize exoplanetary systems and look for signs of life, and lastly, to observe some of the earliest stars formed right after the Big Bang. So as mentioned before, James Webb is an infrared telescope. Compared to visible light, infrared light has a longer wavelength. And however, this is ideal for using a telescope to view the past. Looking at distant things in the cosmos involves viewing them as they appeared in the past, since light moves across the universe at a constant pace. Light is being stretched before it enters our telescopes as the cosmos expands. Light that was first released in shorter wavelengths is extended all the way to the infrared for the universe's most remote objects, including the first galaxies to group together and the first stars to burn in those galaxies. James Webb will be able to see these galaxies as they were just 400 million years after the Big Bang. And that is exactly when astronomers think the first galaxy started forming in the universe. To trace the evolution of galaxies has been a goal of science since the 1990s, when the age conflict arose. At the time, cosmology suggested that the universe was about 8 to 9 billion years old, but there were stars in the Milky Way that were much older. Eventually, this age conflict was resolved by the discovery of dark energy, but this expanded Webb's to-do list. Dark energy says that the rate of the expansion of the universe is increasing, but we have yet to settle on a number for that. And there have been many different measurements, and the measurement is called the Hubble's constant. Webb will try and solve this problem by measuring the Hubble constant using 3 different methods and see how they compare. In its first year, Webb will observe Cepheids, red giant stars, and carbon stars. Then the telescope will try and compare the measurements and see what happens. Studying star and planet formation with Webb will allow us to connect exoplanets to their birth environments and our solar system to its own origins. There are 3 reasons why Webb is ideal for observing planetary system formations. Firstly, infrared light can pass through dust, revealing newborn stars and planets that are still part of their parental clouds. This is important because usually, young stars form relatively quickly from the universal standards, and this doesn't give the parental clouds surrounding the young stars enough time to disperse. And infrared clouds can pierce through these clouds and infrared light can pierce through these clouds and allow us to see what's really happening when these stars form. Secondly, both stars and giant planets begin their lives with structures that contract over time, and both structures emit more light in the infrared wavelength than the visible range, which means we'll be able to see young star and planet formation in greater detail than ever before. And lastly, the infrared range is ideal for identifying a range of chemicals, in particular water and various organic molecules, meaning carbon-bearing molecules. And this will allow us to develop a chemical census at the earliest stages of a planet's formation. When the telescope was first proposed, exoplanets weren't even a thing to be researched. And now Webb's second major goal is to look for Earth-like planets and search for signs of life on them. Scientists now estimate that there is at least 1 planet for every star we can see in the sky. Most known planets today are discovered when they transit in front of their parent stars and block a little bit of light. We can use the amount of light blocked and a sensitive telescope to tell us a lot about the atmosphere of the planet. Webb is sensitive to several carbon-bearing molecules and exoplanet atmospheres that could prove to be signs of life. And NASA has picked out the brightest exoplanets for Webb to observe and detect interesting molecules in those planets' atmospheres. James Webb will begin searching for signs of life in its first year after launch. The chemical composition of the early universe is the result of nuclear processes that took place in the first few minutes of the existence of the universe. These nuclear processes are known as primordial nucleosynthesis. And one of the predictions of this model is that the chemical composition of the early universe is mainly hydrogen and helium with only trace amounts of heavier elements. The earliest stars to form were formed out of this primordial chemical composition. The verification of this model is well within the reach of James Webb, and the way to do this is to measure the metallicities of the most distant galaxies. Metallicity is the measurement of elements heavier than hydrogen and helium. So a low metallicity would indicate that the galaxy contains a lot of primordial stars. One of the oldest galaxies discovered so far is known as MAX 1149-JD1, which emitted light only 600 million years after the Big Bang. One of the first things that Webb will do is to measure the metallicity of this galaxy. And if it turns out that this galaxy does in fact have a very low metallicity, then we know that our predicted model is completely accurate. And lastly, we're just days away from seeing the first images from James Webb Space Telescope. NASA has approved 10 out of 17 instruments for research. One of the key James Webb instruments that have had several modes approved for observations is the near-infrared spectrograph, or NIRSPEC. NIRSPEC is the instrument on the Webb telescope that observes spectra of astrophysical and planetary objects at near-infrared wavelengths. The NIRSPEC grading wheel assembly, GWA, uses diffraction gratings or a prism to separate the wavelengths of incoming light into a spectrum. A study of the intensity or brightness of light across the wavelengths can provide a key diagnostic information about the nature of various objects across the universe, from extrasolar planets around distant stars to faint galaxies at the edge of the universe and objects in our own solar system. NIRSPEC will observe them all. To watch this reveal live, you can watch it on NASA's YouTube channel, where they will live stream and reveal the first observations made by this amazing telescope. A bold new era of astronomical discoveries awaits. And with all that said, I'll pass it on to Sunna.
Thank you, Dhyan. Now that we have background on the Webb telescope and its science goals, we can start talking about what it's going to observe in a bit more detail. Following the successful commissioning of some of its modes of operations, Webb has started to take its first scientific observations and has its first year of observations fully planned out. While much of the data JWST will take will only be released publicly after about 6 to 12 months after the observations are done, there are also many observations that will be released to the community immediately. These are primarily the Early Release Science, or ERS, observations program, with the logos of 4 of the ERS programs on the screen. The purpose of these ERS programs is to allow the scientific community to learn how to best use Webb and its instruments early on in preparation for future data that they will get later this year. These programs will allow astronomers to do useful things like test out their algorithms and data pipelines and to gain a better understanding of how the telescope works and its abilities, all while producing very valuable science. While we don't know exactly what images will be released on July 12th, what we do know is that they will all be part of the ERS observations. There are 13 ERS programs in total, all of which satisfy Webb science goals of studying galaxies, planets, and stars. Webb's first science theme for the ERS programs is studying galaxies. These programs tend to focus mainly on galaxy evolution and interactions, which includes galaxies' central massive black holes and the way that galaxies interact and evolve with their black holes. There will also be lots of work done to find and characterize faint, distant galaxies, including some of the first galaxies to form in our universe. The images on the screen are some of the galaxies that will be observed by Webb as part of the ERS programs, and the images are all taken by the Hubble Space Telescope. Some of these targets include a massive galaxy cluster called Abell 2744 and 4 galaxies which are disturbed from interactions with other nearby galaxies. In addition to these, Webb will also observe bright infrared galaxies and luminous quasars. Moving on to its second science goal, it's planets, both planets in our solar system and exoplanets orbiting other stars. The ERS planetary observations include observing exoplanets, which is spectroscopy and direct imaging of exoplanets and their debris disks, in addition to some other things. Some examples of direct imaging of an exoplanet is shown on the screen, which shows a video of 4 exoplanets orbiting a young star. There will also be observations of the Jovian system, including studying Jupiter's atmosphere and internal structure, as well as its ring system. Webb will also observe Jupiter's moon Ganymede, which hosts a massive subsurface ocean, which sparks hope for the possibility of life on Ganymede. Finally, the third science goal that I'll discuss today for the ERS programs has to do with stellar physics. These observations will do several things, which include studying the properties and production of dust in young stars and search for complex organic molecules created in colder areas of star-forming regions. Some of the objects that will be imaged by Webb are shown on the screen. There will be observations of nearby star systems and star-forming regions, nearby small dwarf galaxies like the WLM and Draco 2, and the amazing Orion Nebula. Another important observation program, especially to Canadians, is CNUCS, the Canadian Nearest Unbiased Cluster Survey. As a reward to scientists that worked on Webb and its instruments, those scientists are guaranteed observing time with the telescope. CNUCS is one of these programs, which will go to Canadian scientists that worked on the Canadian instrument NEARES. It's just one of the several observation programs that Canadian scientists have, and I'll briefly discuss it here. CNUCS will be using 2 of the instruments, NEARES and NEARCam, to observe 5 massive galaxy clusters during Webb's first year of science operations, as well as following up those observations in the next year. CNUCS has several main science goals. These include finding small dwarf galaxies and some of the most distant galaxies in our universe, which are magnified by the clusters. Finding these galaxies will help to study galaxy evolution and how clusters affect galaxies, as well as studying important stages in the history of our universe. The data will also allow for the study of the dark matter distributions of the clusters, which will allow them to constrain cosmological parameters, such as the shape of our universe. CNUCS data is expected later this year, with the first clusters being observed in around September to October of 2022. Unlike the ERS observations, CNUCS data will only be released publicly about 12 months after the data is taken to allow the scientists that worked on NEARES the first chance at using the data. In addition to the ERS and CNUCS programs, Webb will observe many more objects during its first year of operations. Here's a quick summary and a few examples of the things that it will observe, with a couple of the examples shown on the screen. Webb will observe important fields like the Hubble Ultra Deep Field, which have been observed by Hubble and other important telescopes. These fields have led to innumerable discoveries in astrophysics, which Webb observations will greatly build upon. It will observe nearby galaxies like the Andromeda Galaxy and the Small and Large Magellanic Clouds, as well as distant galaxies and galaxy clusters. Webb will observe black holes and quasars such as M87 star and our own supermassive black hole, Sagittarius A star, both of which were imaged by the Event Horizon Telescope beginning in 2017. There will be extensive observations of the solar system, including studying objects like Pluto, Neptune, Uranus, asteroids, and comets, as well as a variety of observations of exoplanets, including the TRAPPIST-1 system, which hosts Earth-like planets. Finally, Webb will also be used to observe sudden, unexpected events like newly discovered asteroids and supernova explosions, which are impossible to predict but provide valuable information to the astronomical community. And Webb's schedule is made to be able to accommodate these observations. This is just the things that we know to look for right now. Many more interesting objects will be discovered in the data this year, leading to many new ideas and new observations for following years. While we wait the last couple of weeks before Webb's first images and spectroscopic data are released, you can still get updates on the telescope. Visit NASA's Where is Webb page for updates on its location and its commissioning. You can also get general updates on the telescope and its observations by visiting the NASA, ESA, and Canadian Space Agency's social media pages, and visit the NASA Webb blog with the link to that shown on the screen. I'll now hand this back over to Dhyan.
Thanks, Sana. Well, everyone, you've been listening to the Illini Carswell Observatory's weekly Teletube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Maheen, Arfa, Nakul, Sana, and myself, Dhyan. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. We'll be around for the next 20 minutes to answer your questions. All of our programs are free, but if you'd like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle at York Observatory, and check out our website for show notes, contents, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in. Clear skies, and have a good night, everyone.